All right, how's it going, everybody? Happy Tuesday. We are going to be talking about section 6.2 today, and section 6.2 is just about computing some volume. Um, on the one hand, I think that this is probably the hardest section that we're talking about so far this class. On the other hand, the good news is that there is not too much new concept in this section. This is just really the extra hard version of the things that we've been doing. And I don't want to sit here and be like, this is going to be so hard. But if I'm assuming you've already read the section, since you're supposed to have done that before you're watching my video anyway, and I'm assuming you found that these are a little bit hairier than some of the things that we've been looking at before. Um, so just some kind of preliminary things before we get into doing some problems today. I've got kind of like four essential examples that I've picked out that I think are mostly representative of what's here. I think there's still a little bit of geometry things you're going to have to do on your own, but I think these are a little bit lengthier problems here. So I've got four examples I want to try and look at today. Um, just before we get started, I think I mentioned this yesterday, but I am still undecided, or not undecided. It's not me that's making the decision. Technically, it's my wife that's making the decision as to whether or not we'll be back by Monday or not from the short trip we're taking this weekend. And so it's possible that next week we're just going to push everything back a day. Technically, this coming Monday is actually a school holiday anyway. If we were in person, classes would have been canceled. My plan was just to sort of ignore that, since to me every day is the same since I'm working at home. But now I'm actually gonna maybe be out of town. So it's maybe the case that instead of Monday, Tuesday, we'll do Tuesday, Wednesday next week for lectures. I don't know. As soon as I get more information, I will let you guys know. So in a Canvas announcement on Thursday or Friday or something, I'll just say to you guys, this is what's going on. So as soon as I get my schedule, I'll let you know. But it shouldn't affect us significantly here. So what are we doing today? Well, today we're just trying to compute some volumes. And the most important thing to recognize is that volumes are just one dimension step up from areas. And we've been computing areas. So our concepts are going to be the same. We just have to track one additional dimension today, is really all that's going on. Thinking in terms of Riemann objects is still going to be the best thing that we can do to help ourselves out here, right? So this idea of a Riemann object, this is a little bit more of a Tony definition. This isn't some formal definition, but I think of a Riemann object as being some n-dimensional object where we can add up an infinite number of adjacent copies. And I say copies because they're not identical to each other. They all change by some infinitesimally small amount, where we can add up infinite copies to obtain an n plus 1 dimensional object, right? And that's what's happening with integration. We're adding up a bunch of 1D sticks, and an infinite number of adjacent 1D sticks give us like a sheet, an area. Now we're going to take all of those 2D areas and add up a bunch of areas, and that will accumulate a volume. So in the same way that we added sticks to get a sheet, we are now going to add sheets to get a volume. It's the same step up. We're just adding one dimension. So let's think about what this looks like generally in terms of integrals. And also importantly, I want to suggest to you that this is not the only integral setup that we can do, what we're going to do here today. What we've been doing up until now is we've been trying to use integration to compute area under a curve. We know that area is length times width, and we know that we've got exactly a length times width in this integral right here. All right, this is just the heights of each of our sticks, and this is the width. All right, so we've got our length times width. Those pieces are literally being multiplied, length times width, within the integral. The integral just says add up all the lengths times widths. Therefore, if we want to get volume, now there's really kind of two different ways to get volume. If I were to ask you what the formula for volume is, I don't think any of you would have told me area times height. But hopefully you're all in agreement that area times height is an appropriate way to state what volume formula is, right? It's area, so that's like meters squared, times another dimension of length. So height is in like meters. Meters squared times meters is going to get us meters cubed. So at least unit-wise, it makes sense that area times height is going to get us there. And I just like to think about, for example, a cylinder, like a can. We can find the circular area of the can and add up all of those circular areas across its entire height to get its total volume out there. Right? So in that sense, we should just be thinking that our integrals now, instead of just listing a height term, f of x, should be giving us an entire area term, which I'm just going to call a of x right here. It's still times another length dimension here, dx. And so this is saying area times length, and that's going to get us volume on the back end. Now, what I kind of was actually expecting, if we were in a classroom setting, I'd be sitting here, we'd all be having a little bit more back and forth, and I'd be saying to you, hey, you guys all know what's the formula for volume, and what I think you all really would probably tell me is length times width times height. And I do want to say to you, that is absolutely an appropriate way to think about this in a calculus setting. It's just the way that you're going to do it next semester. There's going to be a couple of the ones that we can't do with this technique this semester. We're going to need a little bit more of a robust integration method. But if you're thinking of volume as just length times width times height, then hopefully it makes sense to you that we can accumulate that in integrals in some other ways. Here, f of xy, it's a pretty typical thing for us to say things like our z output is what we get from our inputs of x and y. So this is maybe saying x and y is your like on the ground distance, and maybe z is your like off the ground distance, sort of like an altitude. The dimension that you typically don't consider in your current math classes that we would add on, the third dimension, that depth. So this is really just saying multiply up, just like this was your y stuff times your x stuff to get length times width as area. Now we just have dx is length, dx or dy is width, z is height. Now we have length times width times height. That's going to get our volume. In this case, the way that I have things arranged is that we have known. So now you can think of this still as being a Riemann stick scenario. It's just that f of xy, rather than being a stick on a two-dimensional graph that lives here, I'm now picturing my graph as being my flat surface, my table, right? Now I'm picturing a Riemann stick that comes up out of the table. I'm going to accumulate these Riemann sticks first in the x direction, and that's going to form a vertical sheet. And once I have a vertical sheet, I can then add up those sheets in the y direction, and that will get me a solid object. So you can see in this case, I have two infinitesimal dimensions, the x and the y. So therefore, the f of xy says whatever your xy location is on this 2D grid, you should know what your height is. The height is the tip of my pencil that you're seeing over here, right? So we're going to get all the heights, and we could conceivably add up these heights across all the x's to get a sheet, and then add up all the sheets to get a surface volume that we're going to see out there. So anyway, that's some Calc 3 stuff, but you should think to yourself, I know how to make volume. It's length times width times height, or it's just area times one other dimension. This setting is going to work out nicely for us in Calc 2 because there's a single integral. Multivariable calculus is Calc 3, and this is where doing multiple integrals. And by the way, doing layered integration like this is about as hard as doing two integrals. It's really not, when you get to doing multiple integration, there are certainly some hairier parts to it, but directly on face value, multiple integration is just literally just do several layers of integration. There's nothing wildly conceptually difficult about that right there. So in any event, this is a different way that you're gonna get a whole nother section next semester in Calc 3 that's also entitled volumes, but you're gonna do multiple integrals to get those volumes, as opposed to today, we're still, in this whole class, we're always just doing single integrals, but we just gotta recognize volume should be thought of as area times a length versus just two lengths measured together right here. So that's really our core concept that's gonna get us through today here. Area, rather than just a length, is what we're going to need in our integrand. That's really the only thing we need to know for today. The bottom line is really just going to be that determining what a of x is going to be kind of hard, and we need to be pretty good at geometry to get through figuring out a of x's. Doing the integration should be just as easy as it's been for the last 4 or 5 sections. It's finding a of x that's really pretty much our only real challenge today, as well as deciding between should we be doing x things or y things, right? Should we be doing dx or dy bounds on our integral? So let's go ahead and take a look at our examples here. This is certainly best done by doing, but again, I do want to like really say like this is your key analogy for the day. If we can come up with area expressions and add up an infinite number of areas, that will get us a solid volume. So let's jump right into this. First example, and I'm kind of like titling my example right here, but this is just sort of like rules for the rest of your math life. Every time you ever come up on something that's new that you haven't seen before, you should always first try to prove something you already know so that you can feel verified, justified that what you're doing must be correct. The volume of a sphere you may or may not know as 4/3 pi r cubed. And if you didn't, you could at least certainly easily look that up rather than using integration. We want to get a handle on this integration idea, so we're really looking to more like verify this known property. Volume of a sphere is 4/3 pi r cubed. That's the answer we're hunting for here to kind of help validate what we're thinking about. Right? So use integration to determine the volume of a sphere of radius r. One of the other things that I want to say quickly is that you'll notice in this section that in a lot of cases, the book is either going to ask you to do things like say, here are the functions that bound our object, or they're going to do things like in this case, and they're going to describe the object to you, say, it's a sphere. If they're ever just describing the object to you, like saying it's a sphere, then the first thing that you should be thinking to yourself is, the good news is, since I'm just looking at a shape's volume does not depend on where it is located in space. And so it should be the case that you are welcome to place the sphere anywhere that you want in a like three-dimensional coordinate grid, right? Hopefully we are all on board that there is one place that is clearly better than every other place ever for you to choose to place this sphere, right? And that's not the case for all shapes. If we were talking about a cube, by the way, that place is obviously the origin, is where we should center our sphere, right? On the other hand, if we're talking about a cube, and I'm talking about the volume of a cube and wanting to express that with integration, it might be more the case that I want to set my cube to be sitting more like in the first quadrant, because then the corner of a cube, a vertex, would be like at the origin. That might be more convenient there, but kind of just take a moment to recognize that if somebody says to you, like, I need to know information about this shape, and you're thinking you're going to do some calculus to find that information, shapes are not dependent on location in space. And if you're ever given a choice of where to put things, then somehow or another, the origin should very much be closely related to your answer of what the best place for you is to place that object, right? So in this case, we're talking about a sphere. I'm going to put it at the origin, right? So we're looking at a sphere at the origin here. So I'm going to give myself at least kind of like 2D axes here. Ooh, a little bit lumpy of a sphere right there. Man, I got so good at drawing pictures on the board over the last couple of years, and I don't have a board anymore. So what I'm thinking is this. We have still an X and a Y axis. Maybe we're picturing the Z axis as being like the one that like comes straight out from the screen right here. What I'm picturing is that in some way or another, we want to think about two-dimensional cross-section areas of this sphere and add a bunch of them up. I also know that spheres are the literal most symmetric three-dimensional object that there is. Spheres, especially when they're centered at the origin, are the identical object whether you look at them down the x-axis, down the y-axis, or down the z-axis, right? All the views of it are the same. All of the projections are the same. They're a circle onto the three different respective two-dimensional grids that we look at, right? So all I'm really trying to say is there's a bunch of choices that we could make right now that don't matter when we're talking about spheres, because no matter what perspective we view this from, all those perspectives are identical. It's literally just a change of lettering, right? So here's kind of what I'm picturing to myself. The way that I picture what a sphere is it's like somebody stacked up a bunch of circles on top of each other. And I'm going to picture this from left to right. Oh, I almost just want to draw another sphere. Oh my gosh. Can I not draw a better circle here? Nope, I certainly cannot. Okay, so the point is here, I'm going to start thinking about cross-sectional areas, and I'm going to picture this as sort of my first cross-sectional area right there, right? That is a slice of this sphere that I am taking towards the screen, right? I'm taking a slice in this direction, in the Z direction that I'm taking this slice. This slice that's on the left, you should notice, is a circle, and because it's a circle, I know how to compute the area of the circle, and that matters because we just said a minute ago that we want to come up with expressions for area based on the x value or based on whatever variable we are going to integrate over. I'm going to accumulate all my area on this one, just arbitrarily decided as a left to right, as a negative x to positive x type of thing right here. So that's why I pictured this as my first cross-sectional slice of the spheres, because it's the leftmost. It's the nearest to the left x. But what we should be picturing is that we're adding up an infinite number of slices. But the point is that all these cross cuts right here, they're all circles. And circles all have an area of pi r squared, right? So what we want to think to ourselves here is that we want to accumulate, we want to add up, integrate all of the two-dimensional circles which two-dimensional circles do I want? Do I want the ones that are way out over here, or do I want the ones that are way over here? Nope, I want all of the circles that are from from negative r to r, right? I kind of know that's my boundaries of this sphere right here. This is a radius r sphere, so this had better be the x value, negative r, and that's the x value, positive r. Our x value is 1 radius if we are right at the edge of the sphere, sitting right there, right? So a lot of small geometry ideas are going to crop up right here. Now, the next thing I need to do is I need to picture what is the actual area of this sphere. So here's some kind of small things I'm thinking to myself. I'm picturing that I want to come up with an integral. I am picturing for myself, based on the way that I'm drawing this diagram, that I am going to accumulate all of these two-dimensional areas as x changes, right? I have made the decision in this one. This isn't given to me. I decided that I want to work x values from left to right to add up all my cross cuts right here. It could have been that we pictured all of our slices to be vertical, top to bottom, in which case we would have added up all the y values from negative r to r, and all of our circles cross sections would have been these flat ones here rather than the upright ones that we're adding up horizontally here. So what this says to me is that I have made the decision that I want to be accumulating things from left to right. All of my two-dimensional cross sections are left to right. We are accumulating two-dimensional objects along the x-axis. I know that my leftmost x value that I'll experience on the sphere is negative r, and the rightmost x value that I'll experience on the sphere is a radius of r. So I know that my bounds of integration are negative r to r. What I don't know is how to express the area of that circle, very importantly, in terms of x. So let's go ahead and take a look at one of these representative circles right now. The risk about this right now that I have to tell you is that these circles right now are like this, right? They're sort of standing up the way that they're looking at you. Every time I draw a circle on paper, it's going to be the laying down circle. So we have to be very careful that we're smartly thinking about orientation changes here. It really is a pretty visual section here, right? So here's my representative circle. This is a circle. It's not supposed to be any of the one. This is my Riemann object. This is the representative circle that's supposed to represent all of the circles. You should notice that that dot that I just drew right there, that is the x-axis passing through the circle. And stop for a second and stare at the cross-dimension circles that I've got over here and convince yourself that that is true. Okay. Now, the thing that I'm really seeing here is that I know that the area of this circle is something like pi r squared, but I have to be so careful here because r is not a generic letter that I can just whip around all the place. R is the overall volume, radius of this sphere. If I'm talking about one representative Riemann object, you should notice that almost every single circle, there's literally only one Riemann circle, the one dead in the center, that's actually got the same radius as the sphere overall. This Riemann circle has a much smaller radius than the overall sphere right there. So we want to be really careful about how we are measuring the radius of this sphere. And here's kind of the thing that I'm thinking. Where's the picture I drew for this, by the way? I drew a nice picture for myself. I don't know if that picture is going to be as helpful right there. All right, so I'm probably going to have to draw another sphere here to kind of help us out with this. Here's the way that I want to think about this. I want to make sure that when I draw my Riemann object, this is a reference to this image over here. I want to make sure that these are connected. Like I said, the worst thing I could do for myself right now is draw this radius right here and label it R, because that would mean that this picture's R is different than this picture's R, and I don't want to do that to myself. I want to make sure that I'm keeping track of everything here. What I can maybe say to myself here is that the heights of all of these two-dimensional circles right here, they go up to some generic Y value. I might just call this height y, right? So in a sense, the distance that we go from the x-axis up to the y value, down to the y value, that is the radius of each of the given circles that we're going to experience. So it's actually, I think, a little bit more appropriate in this case right here to label this as y, because the way that we've set this up, since our two-dimensional circles are standing vertically, I can measure the radius up. It's the x-axis up to the highest point. Its y value is its edge value up there. And so in that case, our Riemann object's area is going to be pi y squared. Now, there's just one issue with this, which is that this is not an area that's defined by x values. It's defined by y values. So there's a couple things that we can do, a couple different ways that we can think about this to fix our one tiny little issue here, and we're going to be good to go. One thing I can do is I can try and draw a representative right triangle in this sphere. I'm going to try and draw it right now. I think it's going to go poorly, but I want you to see this geometry rather than just the algebra. The right triangle that I'm picturing here is the right triangle that goes up to that corner and drops down. So here's the important thing about that right triangle right there. I'm going to redraw it. In this right triangle, what we've got here for our three dimensions are, this is just however far left and right we've gone, that's our x. This is however far up or down we've gone for that particular cross section, that's our y. This diagonal right here, well, this is actually the one stick that's truly the radius of our sphere, right? This goes from the center of the sphere to the edge of the sphere. This is actually r. And with this triangle, we can establish the relationship between x and y, because I really don't want this in terms of y. I need this to be in terms of x so that these x parts match my integral variable determiner there. So notice here, x squared plus y squared equals r squared. And by the way, that's just our general statement that's true about circles. So what I'm kind of saying is you could have seen this geometrically or not. In any circle, x squared plus y squared is going to be equal to r squared. That's just generic circle truths right there. So I kind of want to solve this guy for y because I really am interested in this stuff being in terms of x, right? So now that I've solved for y in terms of x, I now actually finally have a representation for the area in terms of x. I know it's just pi times the radius of my circle squared. I just did a little math over here that showed that, remember, r is the radius of the sphere, y is the radius of the Riemann circle. I'm just going to literally write that because I know that's confusing in this case over here. R equals sphere radius, y equals Riemann object radius. So again, r is sort of a constant in this problem. I'm just saying a sphere of radius r, right? It might as well have been a sphere of radius 6. R is a lot like a constant in this setting, whereas x and y are the variables that we're kind of fighting back and forth. Because I chose to add up sheets from left to right, that forced my integral to be dx. That forces me to need to be able to write the area of one of those sheets in terms of just x. I can't just go mixing and matching the x's and y's over here. So it looks like now we've got some stuff we can actually evaluate here, right? It looks like I can say, well, now we're going to go from the x value from negative r, that's the left of my sphere, to the x value of positive r, that's the right end of my sphere. What's the area of each of the circles that we're adding up? Well, each one is really pi times y squared. But pi times y squared isn't helpful for me because this negative r to r, remember, we chose to add all these things up from left to right. Right? So we're accumulating dx stuff. And so I really want to rewrite that y the way that we just found out how. Now notice here, we're looking to square y, and y is a square root term. So really this square here and this square root here are going to cancel. And it looks like we're looking at negative r to r of pi times r squared minus x squared dx. So, as I've shouted at you guys multiple times already in the last 2 weeks, I care so much more about your ability to build an integral, especially in this chapter, than I do about your ability to compute the integral. It is obvious to me that the hardest part by far of this problem is getting to just write this statement right here. Coffee, yeah, I am noticing that I am dropping slightly more frames than usual right now. Usually that doesn't stay like that all stream, so hopefully it smooths out a little bit more here. So again, setting up this integral, that's the hard part. Doing this integral, this is going to be pretty easy right here. So let's go ahead and evaluate this guy. Building this is the hard part here. So some things I'm thinking. One, I know that that pi is a constant multiple. I'm just going to bring it out front first. Two, I know that x is my true variable of integration. R is just a constant in this problem here. And so as I do my integration here, r squared is just a constant. And so I'm going to get r squared x minus 1/3 x cubed. And we were evaluating this whole thing from x equals negative r to x equals r. By the way, another reason why it's valuable to write like the x equals right there is because in these upcoming geometry problems, you're going to have x's and y's and r's and h's, and you're going to get some thetas eventually here. Like, we just have a lot of variables floating around, and you need to remember that some of these are treated as constants in some cases, some are treated as variables in some cases. So just keep being good to yourself and good to me and do those things right there, be labeling. Now we can go ahead and evaluate. That pi is just floating around up front. Plugging in r into this guy is going to give me, and so I'll give my two groupings here. This is r squared times r minus 1/3 r cubed minus, and this is r squared times negative r minus 1/3 negative r cubed. So there's my two groupings to evaluate my definite integral. Let's just simplify these two now. This first grouping, I get r cubed minus 1/3 r cubed, and that leaves me with 2/3 r cubed. Over here, we're going to subtract off negative r cubed, and notice here, negative and 3 more negatives makes this positive overall. So I'm getting here negative r cubed plus 1/3 r cubed. So this is going to be a negative 2/3 r cubed as well. And you should notice minus and minus means do addition. And so it looks like in total, what we're going to get is 2/3 and 2/3 is 4/3. We'll bring our constant of pi in there, pi r cubed. And that is exactly the known volume of a sphere right there. So we just built an integral to represent the volume of a sphere. The way that we did it was we forced all of the expression for the sphere's information to be in terms of one variable. We needed that a of x right there. Next semester, it's going to be totally fine for you to use two variables, x and y, to represent your any pieces of your information, because you will be able next semester to integrate over multiple variables. Since we are only doing single integrals all semester, we need to get everything into single variable expressions to express those amounts out there, right? So in general, mostly everything we're looking to do this whole section is just form this integral. The integral from a to b of the area dx or dy, something like that. The big challenge of this unit is, in general, that finding a of x is going to be your challenge. That's pretty much the case here, is that a lot of these problems are 2D and 3D geometry problems, and that the hardest part of most of these for me is coming up with this area statement right here. Doing all of these integrals is going to be about this easy every time. Setting them up is the hardest part. Getting to this statement right here is what I would consider to be more than half credit for any of the problems. This is probably 2/3 credit to get to here, and probably 1/3 additional credit to get to the final part down here, because I know by now you can evaluate integrals. Building them and understanding that this integral is equivalent to this diagram, or a better, smoother version of this diagram, that's the big key concept that we're looking to take away here. Right? So this is our first simple example. I directly copied this. This is example 1 in section 6.2 from the book. But I really like these things. You know, I really do like our book, by the way. Out of all the textbooks I use to teach all my classes, the Stewart Calculus book is the one that I probably think agrees the most with what I have to say about these classes. I really do like that the Stewart book does things like just prove things you already know. And I think that a huge thing in math, as I shook my fist at you guys in week one, a lot of math is really the science of perspective. Being able to change your view as to how you see a problem is usually enough to get you to solve it rather than needing a new tool. It's really a change of perspective that's obviously that is typically the most helpful. And so a lot of times when we get a new perspective to help us understand that we're viewing the same problem just from a different direction is to do a problem we've done before. In this case, say, what's the volume of a sphere? Because we have a known answer, we get to feel real good about the techniques that we think are going to be valid because I see that our new technique did lead me to something I already knew was true. So this is just to say we don't just do math to find out new things. We sometimes do math to verify that even our ideas are correct. In a sense, I've softly proven that our strategy is correct right here. Otherwise, it seems pretty unlikely that we would have come up with the correct answer right there if this wasn't a good method, right? So there's our first volume. We want to do integrals of area to get volume, just like we do integrals of length to get area. Hopefully my diagrams will slightly improve, but I don't think so. It's all right. We're going to pop over to Desmos for some of the harder ones. So what a lot of this section is about, though, a lot of the problems in this section have to deal with rotation about an axis to develop our areas, right? There are some other ones that don't deal with this rotation about an axis idea, but I think a lot more of those follow this trend a lot more closely. So I think this is a good representative example for those. So rotation about an axis with disks is going to result in us having disks and washers rather than circles as our Riemann objects. So we're going to look at a couple examples here. I've picked out 3 examples from the book that I think are worthy representative ones right here. All 3 of these are evens from the back of the book, so that you are welcome to do some odds and check your answers and see if those are kind of equivalent to the even responses that I'm getting right here. And man, and I want to say to you guys, like, all of these things are a little bit weird. Like, I really, like, I obviously, like, prepare for class and stuff like that. But, like, half the days that I teach class, I write down my notes for class, but never look at them because just writing them down was enough. We're in territory now where I am, like, keeping my notes handy because some of these diagrams are a little bit tougher, just some stuff like that. So, like, I just want to say, like, yeah, these are a little bit weirder here, and we got to be a little bit more careful. Have some smart pictures, have some smart geometry. There's all good things to go with this stuff here. So example 2, we're looking at number 4 from our section here. We want to find the volume of the solid. The way that we're going to make this solid is we're going to rotate a 2-dimensional region about an axis. Right? So here's what I'm picturing. Let's picture the 2-dimensional situation here first, and then picture how to upgrade this to a 3-dimensional situation. Right? So first things first, I need to be able to draw this curve right here. This I know is just like the curve y equals square root of x, but I know that that inside adjustment says shift right 1. Right? So I know that my y equals square root of x minus 1 is going to look something like this. It's the curve square root of x, but it's going to start at 1 instead of starting at 0 because we shifted to the right one. This is telling me that we're only interested in this shape between 2 and 5. But let's just hold off on that for a second. I think it'll be easier to describe this shape to you before I take into that information into account. So they're very importantly telling us that we are going to rotate this region that's bounded by this curve about the x-axis. So one important little part for my diagram right here is I'm going to do this. And there's my little rotation arrow. That's my arrow suggesting rotate this axis. I'm going to spin this axis. And what I'm going to do is I'm going to end up getting, well, formally in Calc 3, you'll name this object a paraboloid. Right? It's a solid parabola. It's a 3-dimensional version of a parabola right here. This is still our x-axis as it was in the previous picture right there. But notice here that I don't even care that I only had an upper half of this one, because as I rotate this solid around the axis, it's sort of covering all sides, right? So we've fully spun this thing around the axis. So I think that you should sort of be picturing this as, in a sense, like a sideways cup, right? And it is a solid object. I want to know the volume of this. So when you think of this as a cup, don't think of this as like a hollow object. Think of this, I guess, as a full cup right there, right? Where it's got that sort of bowl shaped at the bottom. Now, the only other thing that we want to add in here is that we are interested in this going from 2 out to 5 only, right? So we're going to chop it here and we're going to chop it here. So we're really interested in this inner volume that we've got right here. So the good news is that this problem is going to pan out to work out very similarly to the last problem. The reason why is this. In the previous problem, the sphere was infinitely symmetric. We could have chosen any direction to approach that problem from. I have written the most integrals in my life, dx, and so I accumulated my area along the x-axis. That was a choice I made. In this problem, I think you'd be crazy to do anything different. In this problem, we are naturally set up that the shapes that are easiest for us to deal with are, again, oriented to be accumulated along the x-axis right here. What you can see is that when we take this cross section right here, again, if we choose to slice this way, we're going to get more circles, right? And it doesn't matter that this was the square root shape. This could have been a cubed root shape. This could have been a billionth root shape. This could have been x to the 47th power. If we're rotating stuff around an axis, we're always going to get that our cross-sectional sheets are going to be circles because we did this rotation about the axis right here. So this whole pi r squared thing, or pi times area squared thing, is going to continue, or I guess it's pi r squared. We just got to determine what r means in the context of the problem. Those are pretty consistent things that show up in these disk and washer method problems for these volumes here. So some things I'm thinking again are, I'm going to do what I did last problem, and I'm going to write my so far statements. So far, what I've decided is I know that I want to accumulate a bunch of areas to get a volume. I have decided that I would like to accumulate my areas. I want to grow them in the x direction. I want to get all of the cross-dimensional slices for every single x value that exists from as x goes from 2 to 5. And so therefore it's a dx integral. Since it's a dx integral, I know that I want an a of x expression for whatever this circle is that's my cross area circle, right? So this circle is a of x, right? I need to know what this circle is here relative to, I need to know what a of x is relative to the Riemann circle that we've drawn here. So what we want to think of is that this is a circle, so this should be a circle where it has some sort of radius. I just got to figure out what the radius is. I know this is going to be pi r squared. We just got to say, what is r in terms of x? Well, how do we determine what our distance is from the x-axis in our diagram over here? If I want to know what the distance is from the x-axis is to there, that's like our r that we just drew right there, right? That is our radius of the circles associated with this solid. Well, that's really, really easy. Our r value here is the same as our y value here. It is the same thing as square root of x. And that is our expression in terms of x, right? So I'm going to say all that up here. R is y is square root of x. And so notice that the good news is here is that we have a real easy way to rewrite any of those letters as any other letters. Now, I know exactly how r, y, and x are related in this diagram. So I feel pretty good then that if my area is pi r squared, then my area in terms of x should be pi times square root of x squared, which is really just pi x, right? So the area of each of my representative disks right here is pi x is how much area it has. Dx is the thickness of it. It's actually really like an infinitesimally smashed cylinder. The thickness of the cylinder is dx, right? It's our thinness right there. The area we determined to be pi x, and it's not pi x squared. That was really pi times the square root of x squared for the pi r squared, which is the square root and the square canceled themselves right there. So it looks like, ooh, hang on one second here. What did I do that's dumb? Oh. I see my one small stupid mistake I made right here. And this is just because I read my words instead of reading my math right here. I saw this and I really should have seen all of this. Our equation is not y equals square root of x. Our equation is y equals square root of x minus 1. So let me go back and adjust all these. Square root of x minus 1, pi times square root of x minus 1 squared, and that's going to give us pi times x minus 1. Okay, okay, we're all fixed now. We're good. I looked over my notes and panicked right there, and then and now I see why. All right, so again, our relationship between y and x, I just accidentally read this instead of reading the actual relationship between x and y, which is that guy listed right there. So now I think we can come back to our integral now, because now we've come up with an expression for the area of our single representative Riemann slice. Our Riemann slice in this case was a circle, and it was a circle because we were rotating an object about an axis. That's kind of just got to produce a circle, right? We're rotating about an axis. So now we're on to the easy part. Now we just got to do the integration. So this should be equal to 2 to 5 of area is pi r squared. I'm just even going to write it this way, dx. That's going to be 2 to 5 of pi. We've already determined that this is the same thing as just pi times x minus 1. I know that that pi does not affect my integration, so I'm going to pull that out front first. And holy cow, could I give you an easier integral to do? So let's just bust this guy the rest of the way out. I don't think I have anything else to say about this. I'm just doing a little simple evaluating here. All right, there's my capital F of 5, capital F of 2. Let's just do a little evaluating in here and see what we get. And actually, I'm noticing the first thing I saw on the right-hand side right away is that this is 0, right? 2 squared is 4. Half of 4 is 2. And 2 minus 2 is 0. So I'm even getting a minus 0 right there. Over here, 25 halves minus just 5. I guess I want to write that as 10 halves then. And so it looks like we're just getting 15 halves pi. Or maybe I guess I'd write that as 15 pi halves right there. So again, I'm going to re-stress all the same things here. The hardest, yeah, and literally as I'm about to say it, Coffee Gopher says the exact thing I'm about to say in chat right here. Definitely, the hardest part of these problems is finding your correct A right here, finding your area expression. This integration is hopefully basically trivial to you by now. This is the stuff that was hopefully like literally easy at the beginning of even last week right here. The trick to this is being able to go from a two-dimensional picture to a three-dimensional picture, extracting two-dimensional information from the three-dimensional picture that you drew, and not having any variable confusion along the way. Because again, this has an r in it, even though I'm talking about square root functions. Apparently there's radius that's involved. Like, you know, we want to really like kind of label these things appropriately right here as we walk through these. Coming up with the a of x is your big challenge right here. And so I think these, and by the way, as I sometimes like to like guide you guys with questions, I think a very appropriate thing to kind of ask with these questions is to say things like, I understand the two-dimensional image, I think I have an idea of the three-dimensional image, but I'm having a problem building the appropriate a of x function to perform my integration, stuff like that. Like, I expect that's where the roadblock is for a lot of these problems right here. Because that is the roadblock, I would also encourage you guys to do things like make statements like these first two integral statements that I made right here. These are telling me, and here's the deal, maybe you just get super duper stuck on one of these problems on like a test, right? And you just can't come up with the a of x. you can still absolutely tell me that you understand things that are going on here, like saying, well, I can tell in this scenario I want to accumulate my area in the x direction, and the x values will start at 2 and end at 5. And if I could come up with how to represent the area of each cross sheet, I'd be good to go. This is a great way for you to literally not be able to do a homework problem or a test problem and still get a bunch of points, because you've explained to me exactly what you do know and what you don't know and how limiting that one part is. Like, that's a lot of information that you could be telling me there. Even saying this, saying, I know that my cross-dimensional slices are going to be circles, is now what this is telling me. That's even more information. Even though you still don't know how to do the problem, if you could get to here and even label where R is in your picture, holy cow, then you're doing really good right now, right? You're 90% of the way there to knowing A, which is 95% of the way to being done with the problem, right? So understand that the hard part of this problem is the two-dimensional area term. Like, that's really important for us to kind of focus geometrically on that. The integration is not going to end up being your problem in any of these here. It's going to be finding that smart cross-sectional area. So the other thing I'll say, since we've done two examples now, is that these first two are very similar to each other. Both of them were essentially the integral of pi r squared. We had to swap out some terms for r, but they still just amounted to being even, just integrals of polynomial functions. Like, it literally does not get easier than that in this class, right? So the calculus here, super easy. Calculus concept here, still pretty easy. Doing the geometry to get from the calculus concept to the calculus execution, slightly more hairy. And I even made a small mistake because of the stupid things I wrote over here. So again, let's just look at some more problems here. And now we kind of know what's going to go on here. We're going to take a two-dimensional image. We're going to turn this two-dimensional image into a three-dimensional image. We're going to attempt to extract a smart representative two-dimensional cross-section of that image and add up all of those two-dimensional cross-sections with integration. Right? That's our big step-by-step process here. Let's do some more examples. So now we are going to, importantly, with this axis, our big difference with this one is we're now doing number 12 out of the textbook. And the very important thing here is, rather than rotating around the x-axis or the y-axis, we're going to rotate around a completely different line. We're going to rotate around the line y equals 4 right here, right? So this is going to make how we measure. So what's going to happen is we're still going to get pi r squared stuff in here. But the way that we're going to measure that radius is going to end up being a little bit different, because we are not rotating around that same just an axis line right there, right? So as usual, let's draw the important pictures. I want a two-dimensional picture and sort of a three-dimensional picture maybe here to go with this, right? So find the volume of the solid obtained by rotating the region bounded by the curves y equals x squared and y equals 4. So y equals x squared. So there's y equals x squared. That's my one curve. I also have the line y equals 4. And this is the line about which we are going to rotate this thing, right? There's my about the line y equals 4. So the solid that we're generating is going to be like the solid version of the bottom half, plus another copy of it up top, because we're rotating around like this. Right? Our rotation is happening here. So one question that I might ask is, like, what's the maximum y value that our solid is going to reach? Our solid should get to a y value up here of like 8. Does that make sense? Because we're going to go, this y equals x squared is going to go from y equals 4 down to 0, 0. But as we rotate it around, this vertex point is going to have made it all the way around to the height of 8 up here when it's flipped, right? So as we rotate around this thing, you should be picturing that we're getting this y equals 4 line right here, and there's going to be our parabola here, but there's also going to be sort of like a copy of it up here, right? And this is the thing that we might want to grab some slices of. Now, I'm going to go back and I want to redraw that whole thing a little bit bigger, because I want to emphasize that we kind of have some choices right here. Rather, I might not even draw bigger, but I'm just going to draw two different pictures. By the way, this isn't a circle. Those two, I know that these slopes here aren't vertical. That's still a parabola where they're kind of going out and out right there. So this actually is like a hard corner, like a cusp right there. And the thing that's occurring to me is that I have a choice to make here. This is my y equals 4 line. This is my y equals 4 line. I'm trying to draw my 3D pictures right now. But what's occurring to me is it seems like I could either set myself up to do some integral from 0 to 8 a of y dy, or, right, and then now in this case, oh, excuse, yeah, because my y values here are going to go down to y equals 0 to y equals 8, and I could add up cross-dimensional circles from top to bottom. The thing that's going to be tough about this one right here is this is going to force us to measure left side of the parabola to the right side of the parabola. And that's maybe a little bit, I don't know, I guess that's doable right there. I think that we are going to want to think about this one in a different sense here, accumulating some vertical circles right here. Maybe we should be doing this one though also. Maybe I'll come back to this one. Our other option here is to take this solid and to picture our Riemann circle to be a vertical circle that we're sliding across, rather than a horizontal circle that we're sliding down. In this case here, we would ask ourselves, what are the bounds of integration for our a of x dx going to be right here? Well, I know I can ask myself, like, what point is that right there? If the height is 4 on y equals x squared, then it should be that 4 equals x squared. So it's going to be plus or minus 2 are going to be these x values right here. So I can see here that if I'm going to build an x integral, that it looks like this region that's bounded is going to go from -2 to 2. So it looks like these are really my two choices of integral that I could set up here. I could either find an area for a cross-sectional circle in terms of y and accumulate them vertically from 0 to 8, or I could find a vertical cross-section and accumulate it horizontally from -2 to 2. Either of those is going to give me the shape that I am interested in here. So I think that I want to do this second one right here. I'm going to do this one. So I'm going to just like, I don't know. I'm just going to say, let's do the dx version. So again, whenever you see dx on an integral, what that means is that you are accumulating area by sliding along the x-axis. So in this case, we have a sheet that sticks out, and we are sliding along the x-axis, getting that sheet. Every x value, all the infinite number of x values, they all have their own sheet that has a slightly different area than the others out there. So what I'm sort of picturing here is sort of like I want to get like this Riemann stick in a sense, right? So there should be this circle right here. But the little bit weird thing is that these heights are a little bit weird, right? This is like y equals 0, and this up here is like our height of like y equals 8 up there. So what I kind of need to do is be a little bit more careful about our bounds on this thing. This is our x equals -2. And this is our x equals 2 right here. So these are the sort of the bounds on where our object is going to live, no matter how we want to think about this guy. So I want to come up with this area of this circle right here. Yeah. So here's the thing that I'm noticing. I'm going to take this cross-dimensional circle right now. I do want to notice that this is the axis y equals 4 that's passing through it. Since I can tell it's a circle, I'm going to label it with a radius of r. Our job is to find out what that radius of r is going to be, right? So we know that we want our area to look like the integral from -2 to 2 of a of x dx. We still are going to do another pi r squared dx. Our goal is just to get r in terms of x once again, because we want to accumulate these areas in the x dimension. So let's just stop and be very careful with this one. I would like to point out to you that I did this one wrong when I did this earlier, and then I was like looking at this and looking at an answer, and like they didn't match, but they were close, off by a constant multiple. That was easy for me to see. So we want to stop and make sure that we're a little smart, a little careful about how we want to do this. So here's the thing that I'm picturing to myself. I can think about what this radius of this circle is going to be, and I'm picturing it in this diagram over here. An important thing to notice is that you should notice that this is the equivalent to this right here, right? Like I can picture either of those to be the r in my diagram right here. So what I'm noticing here is that to get my radius right here, I can go ahead and look at, it looks like this height that I'm experiencing right here, this height that's right there, this is saying go all the way to the height of 4, but then subtract off any height that you've experienced because of your parabola. I'm going to say that again. The length of this stick is the height of 4 minus the height of the parabola at that point. So the height overall is 4. The overall thing, so it's sort of like saying, I guess here's what I want to chunk this up as. The overall height is 4, right? That's the height from 0 to 4. Our term of interest is r. That's what we're working with right now. We want to express r in terms of x instead. What I know the height of this parabola is at any location is y. The height of this thing is y, right? Also known as x squared. So it looks to me like I can say that r is going to be 4 minus x squared. And for the third time out of 3 this lecture, I hope that you are all in agreement that the most uncomfortable part of this problem is stating what your a of x is going to be in terms of the proper variables. Right? Be very careful when you are measuring this right here and play these little games. Give yourself these interval widths right here and mark every single length that you know. It might be the case that you're drawing a 2D graph, two 3D diagrams, extracting a 2D diagram from the 3D diagram, drawing some separate lengths for the 2D diagram that came from the 3D diagram that came from yeah, in a sense, I'm all over the place, but every time I need a new term that's based on old terms, I'm always drawing myself a picture that helps justify what term it's going to be. Let me take a moment from doing this to talk about the homework that's going to be assigned for this week here. I'm going to post our homework this evening for this week. I've been working on writing our by hand homework. One of the things I'm going to shake my fist at you about at the beginning of the by hand homework is that my intention for our by hand homework is going to be that it is a little bit more about communicating math than about just doing math. You need to practice these things because these are hard and these depend on intuition, and developing intuition takes time and effort. There's no way around that. There's not like some smart way that you could learn all this stuff where you could do 3 problems from this section and actually be good at computing volumes. There's not a person on earth that does that. You have to see all the different things that can happen. That takes time and practice. That happens in my open math. This week, you're going to get your first by hand homework assignment, and the agreement that we are all going to soft agree on, and when I say soft agree, I just mean I'm telling you that I am assuming that you are agreeing because it's an agreement that I am making for both of us, is I am going to keep our by hand homework assignments relatively short as long as you all do pretty dang good. So what I'm looking at right now is sort of a mess of a hodgepodge of diagrams on my page right now. What I am asking all of you to do is to do these problems, see all the parts, and then stop and say, oh, it maybe looks like I'm a serial killer if you really go back and look at my notebook based on the way that nothing is organized sensibly. I just put stuff where it came up. After doing this problem, if I were to submit this problem right here as my by hand homework, I would not turn it in this way. Please don't turn in stuff that quite looks like this to me. I want this to be more well organized. And the point is, you don't know the 6 diagrams that you might have to draw to get through this problem when you start it. But by the time you've gotten to the end, gotten an answer, checked that your answer matches everybody else's, you can maybe stop and think to yourself and say things to yourself like, okay, well, this diagram I drew, I didn't even need. Maybe all of these diagrams are more smartly organized in like a sequence at the top of my page or as a vertical column or whatever it is that you say. The point is, sometimes when things get rough drafty enough like this, I really do mean it when I say, now that you've done the problem, go write the problem in a sensible, well-organized way that you would be proud to present to a stranger rather than just barely okay with handing to only your math professor kind of thing, right? So for these by hand homeworks, I think what you see on the screen right now is a great example of kind of what I hope they don't look like. I hope that you do the problems once and then stop and say, now that I've seen all the pieces, I think I can organize my work in a really smart, more well-organized manner. Leave out the extra parts I didn't need, emphasize the parts that I did need, all that smart stuff. You guys have all done a million math problems by now. If you're in Calc 2, I expect that you have a good sense of what looks well organized and easy to follow and what does not. And that's kind of what I want you to be paying attention to in some of the by hand homework here. This is great for a rewriting. We're doing good stuff. I just don't want to turn in this. Right? So let's finish up the problem now. So now that we stopped and were very careful about what the radius was of this circle, full distance was 4 minus the height of the parabola gives us the remaining height, that's the radius right there. So 4 minus x squared is a good radius for this representative Riemann circle that's right here. Okay. So now that I've got that, we can just do the integration. Nothing exciting is happening now. We're just doing the integral. Negative 2 to 2. Oh, I'm going to pop my pi out front. Radius term is going to get squared, so that's going to be my 4 minus x squared squared dx. One thing, by the way, that I might encourage you to notice is that this graph is exactly perfectly symmetric left to right. This is an even function, so it's definitely the case that since this is an even function with symmetric bounds, that this should be equivalent to just taking 2 copies of just half of it. All I'm saying here is we could instead think of this problem as instead of being from negative 2 to 2, it's really just like saying since from 0 to 2 is the same as from 0 to negative 2, just do 0 to negative 2 and double your volume. That'll be the overall volume because this is symmetric. And we actually had symmetry if we would have went in the y direction here as well. So there's symmetry arguments that can be made. So rather than doing the full bounds of integration, I just only kept the positive, and it's because these were symmetric. If this was like negative 3 to 2, we couldn't quite do this, right? It mattered that these were symmetric bounds of integration over an even function says it's really just 0 to 2, and you can double it up. I'm taking 2 copies of the integral from over only one of the halves of the symmetric bounds right there. So that's maybe our one little shortcut that's worth acknowledging right there. So what are we going to get here? 2 pi. Looks like I want to expand this guy probably. Did I do? Yeah, that is the dumb thing I did right there. I've almost every problem I did in my notes I did wrong first and then got right when I saw my one tiny typo that I made here. So, expect that kind of stuff. So there is no way for me to do this integral straight up right now. If I wanted to do something like that, I could try and do like a u sub. But if I did u as 4 minus x squared, then du will be negative 2x dx. And I don't have an extra x term sitting right there to group up with my dx. So because I go from a power of 2 here to a power of 0, I don't have any u sub that I can do. It's not quite there. So I'm going to go ahead and expand this. 16 minus 8x squared plus x to the 4th dx. Now we can integrate, evaluate, multiply through the 2 pi. And I'm going to get 16x minus 8 thirds x cubed plus 1/5 x to the 5th. One of the reasons why identifying that symmetry trick is really nice here is because we are integrating a polynomial. And when we integrate polynomials with a bound of 0, the bound of 0 always goes to 0. Because even if there's a constant term like 4, it will be, or like 16, I should say, it will always get included in x part. So now every term has an x in it. So when I plug in 0, the whole thing goes to 0, right? So all I'm going to get here is 2 pi times, and we got our first grouping is 16 times 2 minus 8 thirds times 2 cubed plus 1/5 times 2 to the 5th. That's our first grouping minus just 0 over there. I plugged in 0 and I can see I'm getting 0. So now we just got a little bit of crappy math here to do. I was wondering where that came from. So 2 pi, what do we got here? I got a 32 minus, that's 8 times 8 is 64 thirds plus 2 to the 5th is 32, so 32 fifths. Man, I wish we were getting common numerators instead. That'd be a lot easier here. So you can see that we're going to get a common denominator of 15. What I got when I did this earlier was 512 pi over 15. So maybe stop and confirm that. This is what I think we should be expecting to get for our answer right there. I'm not going to redo my fraction math right now. I'm assuming you guys can do that part right there. Um, so again, notice we're getting a lot of pies in here, but that makes sense because we keep on adding up lots of circles to make lots of our areas out here. Um, Again, I do think this problem would have worked out this way. In this case, the one thing maybe to notice is that we would have actually had to have broken this up. This top curve right here is really the curve. Let's see here. If this is the function down here, if this is y equals x squared down here, this is really the curve. This starts at 8 and opens down. This is really y equals 8 minus x squared. So if you were going to do this guy, you would actually have to do the integral from 4 to 8 of 8 minus x squared, and then do the integral from 0 to 4 of just the x squared right there would be a little bit different. So I think one of the good reasons to avoid this one is our representative measure here changes because the function that is our boundary for our representative Riemann circle changes here, whereas it did not change in this guy right here. So this is just like last class's video. Pick the one where you don't have things switching on you in the middle of the problem, right? But I do think this would have been totally reasonable to have done this way. We would have had two integrals instead of one. I don't think, they would have been pretty easy integrals here as well, right? So again, finding your appropriate cross-dimensional slice in terms of the variables that you want, that's our challenge. And we're going to get one more of those right here that's going to still be the hardest part of all four problems today. I think determining that cross-dimensional area slice in terms of the appropriate variable is our biggest challenge. So let's look at our final example of the day right here. Okay, I feel like I'm pretty happy with my time right now. I was kind of worried this is going to be 2 hours today, and I think hour and a half is going to be perfect here. So we've been coming up with what we refer to as disks, and I do want to kind of let me actually walk back 1 second real quick. What we're doing in all of these examples right here is really, I keep on referring to this as a two-dimensional object, but I do think it's worth it, and I did say it once, to picture this. There's no way I can draw this. Oh, okay, that wasn't too bad. You really should be picturing all of these. I mean, this is sort of like we're adding up, rather than like, all right, I'm going to say a bunch of not true things here, but here's the way that we think about these things. We think about paper as being two-dimensional. I know it's three-dimensional. I know it has length and width and height. It does have thickness. Since we don't have devices that can easily measure the thickness of paper, we sort of think of it as zero thickness, right? But we all know that if we add up a stack of paper, we truly do get some like thickness there, right? We do get both. I think a better thing to think of here, rather than thinking of these as being circle pieces of paper with no thickness, is maybe it's better to be thinking all of these as like dimes. These are all coins, right? These all do have an area, but they definitely have a measurable thickness. How thick is this thing? This is technically a cylinder. Well, it's technically it's technically delta x thick, right? That's the thickness of each of our coins. It's pretty dang thin, but it's not infinitely thin, right? And if you guys go look at all the diagrams in the book, they'll show it where the first diagram looks like where it looks like they're going to make a circle out of cylinders that are really more like 4 quarters stacked together. Then they go down to like 1 quarter. Then, and when I say a quarter, I mean like the unit of money, like a metal quarter that you hold in your hand. And then to much, much thinner and thinner and thinner sections, right? That's just our letting the number of subdivisions go to infinity thing out there. So it is good to think of these maybe as being not one-dimensional, but as being sort of like our two-dimensional. So in any event, they refer to these as disks because these are really just like really smushed cylinders. They get down to being infinitely thin when we do our integration, but it's good to think of them as technically having like delta x thickness once they're smushed down there. A little very thin, but still technically some thickness, right? So in general, this method collectively is usually referred to not just the disk method. We've done the disk method 3 times now. Now we're going to do essentially the same idea, but we're going to accumulate washers instead of disks. So if a disk is like a dime or nickel or quarter, a washer is like, for those of us that are not in construction, a washer is like with bolts and screws and nuts and washers, right? So it's basically like a dime that we have just drilled a hole through the middle. So there's a gap in the middle. Or if you will, a donut that has been squished down into being a cylinder, right? That's what we're looking at here, stuff with a hole in the middle. So let's see that sometimes when we do this rotation, we end up with a washer rather than a disk. But those are very, very, very similar ideas to each other here. So this problem sounds the same. The verbiage for this problem is the same as the others. I can't detect that this is a washer problem by reading these words as compared to the previous. We're going to need to draw a picture here first. So find the volume of the solid that is obtained by rotating the region that you get when you that's bounded by the curves root x and x. The rotation will happen around the line x equals 2. So let's not think about the rotation at all first. Just think to yourself, what is the region that is bounded by the curves y equals square root of x and y equals x? I can draw both those things. Oh man. All right, my graph drawing's picking up a little bit here. All right, all right. There's my square root of x. I'm going to ruin this whole thing with x. Oh my gosh. Can Tony draw all of a sudden? All right. So, don't worry too much about this later stuff out here. So, a couple things I know. One, this is my root x function. It's my y equals root x. And this is my just like y equals x function. I know, I don't need to do any algebra to know that where these guys intersect each other right here is going to be at 1, 1. That's clearly the point that agrees with both of those curves right there. If you need to do algebra for it, then you need to do algebra for it. But I think hopefully that's pretty obvious right there. So I know that the region that we're discussing is this guy, right? This is the region that's bounded by those two curves. What we're going to do is we are going to take a vertical line, x equals 2. And you should notice, x equals 2 is like way out here. This is our line about which we are rotating. So what's going to end up happening is this this two-dimensional shape that's over here, as we spin it around, you should be picturing that we're getting other parts of it that are over here, right? I'm picturing the rotation happening like this, about this line x equals 2. So the thing that you should notice is, in the previous examples when we did our rotation, there was stuff touching the rotation of axis. I got to scroll back up and show this stuff here. We are really comparing this problem to the previous two. In this problem, we rotated this curve, we found this region of interest from 2 to 5, and we spun it about the axis. But the important thing is that our region of interest, which, gosh, I kind of drew a little weird in this problem right here. Our region of interest here was the part from 2 to 5. The important thing here is that our two-dimensional region of interest was touching our axis of rotation. Therefore, we got whole circles as our Riemann object. In our second example, we rotated about an axis, but our object, our two-dimensional object that we were accumulating to make a volume, it was touching the axis of rotation. So there was no gap between the two-dimensional object and the axis of rotation, and therefore there was no gap between our axis of rotation and where the solid started to form. In this third example, we are rotating around an axis that is not at all touching our region of interest. That means that when we spin this thing around here, even when we look to the other side, the nearest our solid will ever be to this central axis is 1 unit away at all times. That's the closest it will ever get. It will never touch, right? So what that means to me here is I am sort of picturing for myself that I have like a mirror image over here, right? I can't draw this three-dimensionally, right? Maybe what you should picture is the bowl that we had in problem 2, but picture chopping the bottom out of a bowl so that it wouldn't actually hold water, right? So you have like maybe like a semicircle bowl, but you like saw off the bottom of it, right? That's what we're really getting here, where there's a center spindle that doesn't actually touch any of the chopped bowl that's remaining, right? You have a minimum distance that you need to go. Even if at its closest at the very bottom of the bowl, it's still some unit away of some stick that would be sitting in the dead center of that bottom chopped off bowl, right? I know I'm using a bunch of ridiculous words here like bottom chopped off bowl, but it also really matters that you picture these things in your head, and it's very helpful to picture everyday objects that this is like equivalent to here, right? So what I'm sort of picturing then is that there's sort of like another copy of this over here, right? And really a three-dimensional one all the way around, right? I'm just showing if we're really taking a cross-section of this three-dimensional object, there's really going to be parts of it on both sides that we're seeing that cross section of, right? So what I'm picturing here is that when we accumulate our stuff, like if we were to accumulate things top down, as I think will be best in this problem right here, you should notice that top down before would have given us like circles right here. But now there's a gap. My circle doesn't even start until it gets to being 1 unit away in each direction. So my representative Riemann stick in this case here that I'm wrapping around, here's the Riemann stick that I'm going to rotate. That's the stick that's getting passed through a third dimension here and is going to rotate all the way around. And we're going to add up the rotation of that Riemann stick for all of the y values that we're experiencing here. So what we need to decide now is what is the shape of the two-dimensional object that is swept out by this one Riemann stick being spun around the axis here. So what I'm seeing here is as I spin this Riemann stick around, so I'm going to say here rotation of general Riemann stick is we're taking a stick about an axis and rotating it around that axis. And what that's leading us to is a washer. The problem with this picture is that I just sort of flipped some stuff. And it's hard for me to say that. All right. Here is that Riemann stick. Oh shoot. Okay, hang on. Let me. So this is a delta y. So let me kind of reference some things with my picture here. This stick I'm calling a delta y vertical height, and that's just because I drew this Riemann stick exactly like that in the picture. It's got a change in y as the height. What we know is that we need to come up with the width of this Riemann stick so that we can come up with the area of this washer right here. So maybe what I should do is this. Here's what we're really trying to come up with. This is our single washer now. This was the circle that we were drawing in the past. This is now a washer because we have spun it around. I do want to say it should be laying down to match the Riemann stick. Does that make sense? So that's a standing up washer right now. Let that washer fall flat onto the table. That's the washer that I was imagining us getting as we rotate around that center spindle here. So maybe here's my visualization of it. This axis of rotation right there, I'm picturing as my pencil. And I am taking a stick and spinning it around my pencil. That's going to create a washer because there is a gap between the object and the center of the rotation, the axis of rotation right there. So if you let this washer lay down flat, then that would give you, maybe to help my diagram right here, this is that center of rotation. The rotation is happening around the axis that direction. Here you see the axis vertical. Here you're looking straight down on the axis in that diagram picture right there. So a couple things we need to know. What's the area of a disk versus the area of a washer? Well, area of a disk is easy. Disks just have a radius, and it's just going to be that area is pi r squared. We need to talk about an area of a washer, though. It's a slightly different thing. Fortunately, we still just need to know about circles. Typically, the way that these are denoted is, I'm going to try and draw these gaps more. Typically, we write these with a little r and then a capital R for the entire radius out there. So the area of just the, just the washer itself, I don't want the inside parts, just the washer itself. It should be the entire area, which is pi r squared. That's the whole area's circle on the outside. Take away that little inner area right there, and that should be our pi little r squared right there. So if you can see those labelings right there, that's my capital R for the entire radius. This is my little r for our small radius to the inner radius. So inner radius and outer radius are maybe our better words for those right there. So the area of a washer should just be the difference of two circles areas. It's the outer circle minus the inner circle. And that's all I did right there. Circle area minus inner circle area right there. We just got to keep track of outside minus inside stuff right here. So what we're saying that we've done is we're developing a washer that's associated with this Riemann stick. And we would like to add all of those washers vertically. And I know that we're adding them vertically partly because our axis of rotation was a vertical axis of rotation. So some things that I know now are, it looks like we should be building a integral that is going to be dy. I need my washer area here. It looks like my bounds of integration are, and again, this isn't stuff that's given to me. I've got to figure this stuff out. But from the problem here, I can see that the region that is bounded by the two curves has a lowest y value of 0 and a largest y value of 1. So again, that's on you to determine right there that those are the point of intersection. They're trying to give you nice functions so that they have very obvious points of intersection right there, so that we know where that's kind of starting and ending right there. Okay, so all we need to do is come up with a washer area in here in terms of y, and I think we're good. So let me kind of bring that idea down here. So we want now, I want for my volume to be the integral from 0 to 1 of the washer area in y dy, right? By the way, more math Tony things here. Why wouldn't you just write integrals with words in them like that? There's nothing wrong with a variable being a phrase of whole words rather than just a single letter. I think people feel too trapped into obligatorily using one letter variable names, and that is just crazy. If you just want to write an expression in here, and again, back to this whole if you get stuck on a test thing, this is a really smart thing for you to write, even if you can't do this problem on a test. A really smart thing. This tells me that you know so much about this problem by you just writing this stuff right here. This has to be at least half credit for this entire problem right here. I mean, this tells me that you know that volume is going to be an area, telling me that I know that this needs to be an expression in terms of y because we're integrating dy, understanding that the y boundaries are going to go from 0 to 1. You had to have worked that out of the equation, stuff like that. Like, this is a pretty advanced statement to make, whether you even understand the washer situation or not. Right? So this is good stuff right here. Writing those words in there, there's absolutely nothing wrong with that, and lots of things right with that. So get comfortable with that. Like, you don't need everything to be x and f of x. Like, it's a little bit of it's good for technicalities and to make sure that you can communicate with all people, but like, words is good. This is a good description here. So if we can come up with this washer area in terms of y, we're going to be pretty happy right here. So here's, I guess, what I'm thinking. I kind of know what my outer and inner distances are. I want to know what distance we need to travel. Like, I want to know the width of this. And the way that I can get the width of our Riemann stick, this is the like thickness of our circle right here, would be to find this distance here. This is our outer radius. This is our inner radius. So I'm going to label this as capital R. That's our outer radius, is getting all the way to the outside of our Riemann stick. This guy right here is going to be a little r. This is our small, our inner radius, the radius that you need to travel to just even get to touching the solid at all times, is little r right there. So the question is, what quantities do we get for this? Sorry, I did a dumb thing right there. I stopped at 1. Let me just back each of these up. Okay, I'm doing the right thing. I just stopped these at 1. Our axis of rotation is at 2. I needed to go to 2 right here. So our outer radius of this washer, the far outer radius, is that capital R that I drew earlier. That's my capital R right there. The full radius to get from the absolute center, which is where we measure circles, to the outside edge is capital R. To the inside edge is lowercase r. right? That's how I generally denote these. Capital R, outer radius of the washer, lowercase r, inner radius of the washer, as we just did a moment ago. So it looks like what we want to know is what overall is this distance that we're going to be experiencing right here. Now I want to write these a couple different ways. I'm going to write this the long form way, but I'm hoping that a couple of you guys are smart and see this the short form way. So I'm going to do this sort of the longer form way first. What I am seeing here is I just made this phrase here, the area of a washer is just the pi r squared minus pi r squared, where one of the r's is the outer radius, the bigger of the two radii. The small r is the smaller of the two radii, the inner radius right there. So what I can do is I can find what really should be this r value right here, capital R. Well, it looks like what capital R is to me is it says, capital R says, go the full distance to 2, just chop off whatever square root of x is here, right? That makes sense. Similarly, here, for lowercase r says go all the way out to 2, but go ahead and chop off this initial part. And this initial part right here will always just be however far you went out in terms of x. So those are my big and my small radii right now, 2 minus root x and 2 minus x. But the thing that you guys know that we need to do is we need to write these in terms of y actually here. And so it's important that we kind of update these things right here. Maybe it's better for us to actually think about this as x equals y and as x equals y squared for these guys right here. Actually, I think I actually made a bad statement right here. That shouldn't be a square root right there. And the reason it shouldn't is this. Our large radius here is going to say go all the way out to 2. Just subtract off whatever the x value is that's associated with that boundary right there. What we want to do is convert that into the y value. It's going to be different based on what our function is, right? So that's where the y value comes in out there. So these should be these two different x values here. Maybe I should really be calling this like x1 and x2. I think this is the smart thing that I should have been writing right here. This is really 2 minus the inner x, and this is really 2 minus the outer x right here. So I think that it's going to make the most sense now for us to make our statements here as integral from 0 to 1 of we want pi r squared minus pi r squared dy. What we just found here is that this should be 0 to 1. Our first grouping was pi times, and what we saw was that we were going to be getting our outer radius. We want to do 2 minus, and I'm going to call this x2, our first curve, squared, minus the inner area. We want to chop out that inner disk. And this should be going from 2 out to our other x function, x1 equals y. So remember, we're measuring x values, so I'm trying to just use x stuff here. The good news is that we know exactly how to express x1 and x2 in terms of y. And so I've got these values available to me now. Our outer radius, our outer term, the x2, was associated with the square root of x function, which when you flip y equals root x, you get x equals y squared. Right? So that's going to be y squared. That's your radius squared minus pi times 2 minus. This was just a y equals x function, so y and x were the same for that guy. So it looks like we have made it here. I want you to notice that there is a ton of algebra that we could be doing here that's going to make this actually a little easier. Here's the maybe slightly smarter thing that we could have measured right here, is that this width right here is really just going to be what we are calling x2 minus x1. Do I have that back? X1 minus x2, I guess, would be the width, because the upper bound is this. Oh no, outer minus inner. Outer minus inner, not left and right. Outside minus inside. So the outer here is the y squared, minus the inner here is just y. So it should just be that this is just y squared minus y. Then we multiply it by pi because it's an actual grouping of a circle. So I'm thinking that this really should amount to pi times y squared minus y squared. Let's see if we get stuff that looks like that done here. So let me bust out another. Wait, is it gonna let me? Okay, cool. It's gonna let me rock and roll on down here. So let's try and do all this algebra. Remember that this is our last evaluation of an integral today. Remember that one of our important things is don't ever do calculus until you can't do algebra anymore. So I'm going to stop and do as much algebra as as I can to this thing to simplify it as much as possible. So 0 to 1. First thing I notice, both of these have a pi involved. It can be factored out front. Oh, by the way, I dropped a squared here. Pi r squared. Oh, and now I'm getting out of order. Already factored that pi out. That should be squared, but that pi has already been factored out. So I think this is what we're really looking at right here. Some more algebra that we want to be doing first. So let's expand this guy. 4 minus 4y squared plus y to the fourth minus 4 minus 4y plus y squared dy. Let's group up all of our like terms. Yeah, coffee gopher. I feel like I did a small, slightly dumb thing that should be equivalent here. Yeah, I'm trying to see if these are going to be equivalent right here. I agree with you. I'm like now skeptical. So some things I'm seeing. I've got a 4. Oh, by the way, I shouldn't have to yell at you guys about algebra things, but you better make sure that when you're doing subtraction, you wrap this stuff up in parentheses and distribute that negative right there. That matters. 4 minus 4, so those cancel. I've got, let's see here. I know y to the fourth is going to be sort of like my biggest term, so I think I can write that one. I don't have any cubed stuff. Let's see. I've got negative 4y squared and another 1 negative 4y squared, or another negative y squared for a negative 5y squared. So I've taken care of this. 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 And it looks like we just need a plus 4y. Yeah, why is this going to be just slightly different than what I was picturing right here? Because I get, that's okay. We can do this integration right here. Let's see if we get an answer that I recognize here. Not doing integrals anymore. We're doing the integral. I don't have an integral symbol. And we're getting 1/5 y to the 5th minus, I'm getting 5/3 y cubed plus 2y squared. Evaluate from y equals 0 to y equals 1. Again, you should love evaluating integrals at 0 when they were polynomial in the first place, because that literally just means, oh man, 0 to 1 with polynomials is the best. That's like, just keep your integer coefficients and add them together. So here I'm just getting 1/5 minus 5/3 plus 2. And let's actually do it here. This should be 3/15 minus 25/15 plus 30/15. And 30 minus 25 is 5, plus another 3 of them is 8. Yeah, so Coffee Gopher is very much pointing out that I think I was doing an r squared minus r squared wrong thing right there. The fact being is that, right, so I'm going to write my equivalent statement that you just wrote right there, is that this is equal to pi times r squared minus r squared, which is not equal to pi times r minus r squared. And I feel like I just did this a very slightly different way before, but I don't. I agree with you that I think I was trying to make a shortcut that I can't make algebraically right there. And I also, by the way, Coffee Gopher, I've read so much LaTeX in my life that if you just type LaTeX, I can just read. It's I'm Neo reading the Matrix with that stuff right there. I can just read LaTeX there. So I think that 8/15 is what we are looking for this guy right here. Um, let's just triple check this real quick. Let me just look at this guy up right here. We were doing, I think this is problem number 16 out of, oh no, this is problem number, yeah, 16 out of the textbook. Oh gosh. 16, yeah, we're doing 16 here. 8, 8 pi 15ths. 8 pi 15ths, cool. I am getting the answer that the book is getting here, so I feel pretty good about this one here. So, as promised, your challenge in this semester is to come up with two-dimensional cross sections that are representative of a Riemann object. In this case, our Riemann object wasn't even really the stick. I drew a Riemann stick, but the important thing here was the Riemann object itself was the washer. This was the thing that we added up an infinite number of copies of. We did spin this stick around an axis of rotation to develop the washer, but we added up the washers. Right? So in this case, the Riemann object of interest was a washer. We compute area of washers by computing the outer area, subtracting off the inner non-existent area. Don't make the mistake that I was trying to force into my problem right there with a little bit of a shortcut. It's totally fine to just do your like pi capital R squared minus pi lowercase r squared. Remember here are other kind of big takeaways from this problem. Because this was being rotated around a vertical axis, it seemed sensible to me to build my washers in a dy integral. Because we were rotating around horizontally, I wanted to accumulate my circles vertically right there. It gave me a bunch of circle-shaped things if I went top to bottom. If I tried to go left to right on this would not really go awesomely here because my object is not arranged left to right really. So the axis of rotate or the direction of rotation being about a vertical axis tells me a dy integral. The fact that my two-dimensional region of interest did not touch the axis of rotation is what told me that this was going to end up being a washer with a hole in the middle versus a solid disk that does not have a hole in the middle as compared to the previous three examples. So I think that these are all pretty much representative of what you're going to see in the book. I just think that the only other tough ones in the book that don't look like this one are ones that are a little bit more similar to our first problem here, where it's really just like, I don't know, come up with something. This one didn't naturally lend itself to any like obvious way to build it right here. It was just saying, can you come up with slices of this thing? And you said, oh yeah, slices of spheres or circles. So yes. So this was a kind of easier one here, but this might be more generically representative of some of the harder ones. I know the book asks you to do things like come up with like trapezoid areas and stuff that are like rectangular, but that's great because you know the areas of rectangles. All the cross sections are going to be areas or rectangles. Make sure that you add them up that you're going to get rectangles as your cross sections rather than awkward shapes as your cross sections. Like make those smart choices for yourself. So I will say you guys have more choices to make with this section. It's not obvious what you need to be doing. I will also say that when you do these problems for your by hand homework, your work is going to look a bit like this, what I would call crap that I just wrote right here. This is disorganized. I have a bunch of things scratched out. I have wrong parts on here. I have parts of diagrams that I didn't really mean. I have diagrams that I didn't really like. I tried to take a shortcut I shouldn't have taken. Uh, like, I don't know. For this screen right here probably looks all fine. This screen up here looks like I didn't know what I was doing at the time, and I didn't because I was just doing the problem for the first time, and that's okay. So I do want you to think about, and this isn't for every homework problem, but on the take home, like the by hand homework, I'm going to ask you to do like 2 or maybe 3 problems for that. And what I want you to do, and again, I don't think I'm asking anything crazy here. I want you to just do them, check your answer, be confident, then stop and say, how could I make this one problem look real nice on like a half of a piece of paper or one piece of paper? It's not going to kill you to rewrite things a little bit, make things a little bit better. The harder math you do in life, the more you should develop this sense of like maybe a little bit of a rough draft type thing. Yeah, yeah. Don't worry, Coffee Gopher. You're gonna see plenty of that. Where in my head, like 2 minutes before lecture, I'm like, oh man, I should totally just do that one shortcut and not realize that it's dumb and wrong right there. And don't get that's the organic part of all this stuff right here, right? So, the other thing I'll say to you guys is that like, so when I was in grad school, I didn't make this transition of like ever rewriting any of my homework until grad school. That being said, I am really well organized with really good handwriting, so I don't think I need to as much as the average person, but once I got to grad school, it became clear to me that things were like everything I wrote on paper was wrong for the first like 6 times instead of the first 1 or 2 times. So I stopped. And so when I was in grad school, a buddy of mine actually found the school had been replacing a bunch of their whiteboards. So they, out by a dumpster, there was a bunch of like classroom size, like massive, like 20 foot by 8 foot whiteboards. So he snagged one of them and chopped them up into like 7 sections and gave them out to a bunch of people. Well, I ended up with 3 of them at my house because everybody collected at my house, and we just had a bunch of whiteboards mounted on the wall. And it basically became standard practice that you do 100% of all of your work on the whiteboard until you know that you're right. Then you just copy what's on the whiteboard smartly onto your paper. So I got to the point where even though I've filled 20 notebooks in my life with math problems on paper, in grad school, I really made a pretty hard switch to doing 100% of my work on something else. I only wrote on paper when I knew that that was my submission in a sense. And I think that's a little bit hardcore for what I'm asking of you guys. I don't want this to be like, don't write on paper until you're submitting it. But like that worked out great for me. And it now kind of bothers me to do loose scratch work on paper. And I like having even just this, my drawings here aren't great, but it makes me feel better. There's something less committal about not being on paper. So I would encourage you guys to start to think that like your math horizons have grown enough that just writing down an answer is not really a good description of what happened anymore. And it might make more sense for you to have better flow and organization and relating your diagrams to the work that you do as justification a little bit more closely than you might have had to in the past. And it's maybe the case that that's slightly overkill for this class, but it probably won't be when you go take Calc 3 and differential equations in the future. So this is more of like, begin to develop a adult mathematical technique here rather than just the more child mathematical techniques that we develop in algebra, where it's like write stuff till you circle an answer, then stop. Like you should recognize that math's a little bit more than that by now, and you should acknowledge that by thinking about organization of your work after you have completed a task. So I think that's all. I've talked about that plenty right here. So I think this is my kind of wrap up here for the day. I agree with Coffee Gopher. I don't think that my shortcut I was trying was even going to work out there. I do, yeah. Let me just do this real quick right here before I close up for the day. There we go. Okay, now we're good. Yeah, so you guys know that I still need to make some homework assignments, so that's what I'm going to do a little bit this afternoon. You guys know that we might be pushing Monday and Tuesday's lecture to Tuesday, Wednesday this week. I don't know about that yet. You just need to know I will be sending you a Canvas announcement on like Thursday or Friday, or probably not Saturday, but Thursday or Friday before we leave for the trip to say this is our plan for Monday. It's either going to say Monday will go as planned, or it's just going to say push everything back a day next week. We won't change any times for anything, just days. And I don't plan, even if we do bump things by a day, I do not plan to change any deadlines for assignments since all of our deadlines are 2 weeks long anyway. hopefully, or 13 days. I hope that you guys can all manage in 12 days what you were doing in 13 before. I'm assuming that that's not too big of a restriction. If it is, let me know. I don't think it should be. So that's all I got for you guys today. Happy Tuesday. This is our last video for week 2 right here. You should notice, just take a quick glance ahead if you're in your textbook, you should notice that section 6.3 is more volumes. This is going to be an alternate technique for accumulating our volumes. Section 6.3 is volumes by cylindrical shell. It is the cylindrical shell method rather than the disc and washer method. So 6.3 is going to be really similar to this. It's just that our Riemann objects are going to be different that we're adding up. But the concept is going to be the exact same. Determine your one representative Riemann object, figure out how to accumulate the infinite number of Riemann objects to get to your total volume. Finally, when we hit 6.4, 6.4 is, 6.4 is work. Awesome. 6.4, we get to do some physics. So 6.4 is a little bit of physics problems. These are really satisfying. I'm assuming at least half of you are physics engineering people, so this should be your focus anyway. Even if you're not a physics person at all, always remember, calculus was invented to do physics. We now know it applies to a billion other things, but at least for historiological purposes, you should appreciate doing physics problems in calculus class. It's the first things that people were ever doing. This is what Isaac Newton did, was physics problems with his calculus, and so that's the reason those are always going to belong in these textbooks here. Okay, that's it for me. I'm going to wrap up the stream here. Happy Tuesday, everybody. Thank you for the people that were in chat. It was good to have you live people here. And I'll go ahead and wrap this up. I will see you guys live again either Monday or Tuesday next week. I'll be sure to let you know. I'll see you guys in office hours or my email or in my open math if you guys got any questions, or the Discord. Hop into the Discord. I fixed the link again. I think it's going to work. Yeah. Thanks for the assistance today, Coffee Gopher, and I'll see all of you guys next week.